Good evening, everyone. We'll just wait for a minute so that other people can join. We were facing some problem with the internet, and that's the delay of 5 minutes.
Hello, can you hear me, Anand?
Yes, correct. I can hear you.
Okay.
Okay, we'll start. So, good
Okay.
evening, everyone. Thank you for attending this webinar. So, for those of you who don't know me, I'm Anand from TESCON, and we are based in Bangalore. So, TESCON has been part of the researching community of India for the past 20 years or so. We have supplied and supported premier research instruments for various organizations in India. We have been contributing majorly to the field of atmospheric research, air pollution control, and so on. Today, our focus will be on real-time measurement of ambient metals and its applications to source identification and apportionment. It is using an instrument called Xact, which is manufactured by Cooper Environmental Services from USA. We have two of these instruments already operational in India. We have today with us Craig Peterson, Vice President of Cooper, USA, who will be presenting today. If you have any questions during the session, you can post a message in the chat box. We will answer you at the end of the session, or we will surely be in touch with you after the session as well. So, Craig, please continue.
All right, thank you, Anand. I'd like to just say thanks for everybody for attending today. Good afternoon in India. I'm in Portland, Oregon. It's quite early here. It's about 4:30 in the morning. So hopefully I'm bright and chipper enough to give a presentation, but I really appreciate all of you coming. As Anand mentioned, we're going to be discussing near real-time elemental analysis of ambient particulate matter and its application to source identification and source apportionment. And very specifically, we'll be talking about the role that real-time elemental analysis with the Xact 625i plays in that. So we'll be talking a little bit about the instrument itself. We'll be giving a description of it and discuss some features of its operation. Because obviously accuracy of your data and your elemental analysis is very important to your source identification and source apportionment. We'll be looking at some of the comparison studies that have been done between comparing the instrument to laboratory reference methods. We'll be talking about some of the quality assurance features of the data on the instruments so that you know that each and every data point is accurate and reliable and can be used reliably in your source apportionment and your source identification work. And then we'll go into some more specific examples of source identification and how the instrument can be used. We'll be talking a little bit about ADAPT, which is a data visualization software package that comes with the Xact that is very useful in source identification and source apportionment. And then finally, we'll be talking a lot about how the instrument and the data from the instrument has been used to various types of factor analysis and source apportionment in air sheds throughout the world. So first of all, the Xact, it's a continuous metals monitor. It is based on X-ray fluorescence, or XRF, and reel-to-reel tape drive technology. It can measure up to 67 different elements or metals simultaneously, including lead, arsenic, and cadmium. And it can give near real-time analysis results. So rather than waiting, 4 to 6 weeks for your results to come back from the lab, from a sample that you maybe got one sample in a day, you can get hourly or even higher time resolution samples with the instrument. We'll be talking primarily about the ambient or fence line monitor, the Xact 625i, but the technology is also available in stack and water versions. This slide shows the different elements that can be measured with the Xact. Basically, anything highlighted on that periodic table in blue can be measured by the instrument. Anything ranging in atomic number from aluminum all the way on up to uranium. Now, our standard configuration with the Xact comes with calibration for 44 different elements, and that's something that would be a pretty standard package that would be available and very useful in doing source apportionment work that provides enough information, enough different elements to be able to reliably identify different sources. But also different configurations are possible, even more elements or even less elements if that's what the situation requires. This slide shows some of the detection limits of the instrument. What you'll see on the left-hand column over here, if you can see my cursor, is the element, and then the detection limit in nanograms per cubic meter. The detection limit is a function of the sampling and analysis time, and we have various different sampling and analysis times available. Anything from, well, actually we go down as low as 5 minutes now, but on the table here we have listed 15 minutes, 30 minutes, 60 minutes, all the way on up to 4 hours. Most of our users in the ambient environment are using 60-minute sampling and analysis time periods. That generally matches fairly well with the type of measurements they're taking for total PM mass. And at this sampling and time interval, what you'll notice down here is that most of your elements are have detection limits under a nanogram per cubic meter, so plenty adequate to do source apportionment work. As I mentioned before, there is also some ultra high time resolution that's available. You can get sampling times down as low as 5 minutes. And we'll be talking a little bit later on in the presentation about some of the applications where that might be useful. This slide here shows a schematic of kind of the inside of the analysis area. What you have here is your filter tape. It's a reel-to-reel filter tape. We use a Teflon filter. And this blue cylinder here represents our sampling inlet. The aerosol is sampled through here at a rate of 16.7 liters a minute, which corresponds to the rate required for PM10 or PM2.5 size, particle size cut points on standard EPA samplers. The air is sampled through there. The particulate matter that is entrained in the air gets captured on the filter tape. The rest of the air gets passed through and is measured and totalized. And then after the sampling period is complete, the tape is advanced over here into the analysis area where the deposit, the PM that's been deposited on the filter tape, is analyzed by X-ray fluorescence for metals content while the next sample is being collected. So what you have is a continuous sampling and analysis cycle that will go on continuously until you have to change the filter tape. In hour-long sampling mode, your typical filter tape change-out period is about a month. So the instrument, in most situations, will run for a month with essentially unattended and give you data for that entire month's time period. So on the next several slides, we'll be discussing some of the comparisons that have been made between the Xact and laboratory analysis methods. We'll talk about 3 specific studies specifically. There are many others that are also available in the literature, peer-reviewed literature. But the 3 that we'll be talking about are the US EPA's Environmental Technology Verification Study that was done several years ago, the ETV program. We'll be talking about a comparison study that was done in the United States at a national ambient air toxics trend station. And then finally, our third study will be discussing one that was done by King's College in London and published in Atmospheric Measurement Technology. So for the first study, the Xact 625i ETV study, the data in this study was produced by the US EPA. It was done independently of Cooper Environmental. In the study, the Xact daily average, so the average value from 24 one-hour samples, was compared to a single one-day sample from a reference method PM10 sampler. And then that filter from that sampler was analyzed for metals by ICP mass spec, or inductively coupled plasma mass spectroscopy. Any data for any element above the Xact's quantitation limit was compared to any data above the reference method's detection limit. And then the Xact's data was plotted against the ICP-MS or laboratory data, and a linear least squares fit was performed on the data set. And in this kind of case, a slope of close to 1 would indicate very good agreement between the Xact and the reference method or the laboratory method, and a high R squared, well, maybe 0.9 or greater, would indicate very good precision or very good agreement between the two methods most of the time. So for this study, there were about 4 elements where that were consistently present at high enough concentrations to make comparisons between the two methods. And I'll show you, there's 2 of them on this slide and 2 of them on the next slide. Here we have lead in the upper left-hand corner over here, and selenium in the lower right-hand corner. And what you can see here is we have the ICP-MS daily average plotted on the x-axis, and the Xact 625 daily average plotted on the y-axis. And then we have the least squares regression fit here that was represented by this line. The slope for lead was about 1.06, so that indicates very, very good agreement between the two methods. And then an R squared of 0.94, indicating very tight agreement, very good precision in that relationship between the two methods. And then here for selenium, we have a slope of 0.986 or almost 0.99, and R squared of 0.93. And in this case, I think it's very, very interesting to point out that we're seeing very, very good accuracy down to the level of a nanogram per cubic meter. These are the levels that were present in the airshed that we were sampling. And then this slide shows the results for 2 other metals, for zinc and for manganese. Again, for zinc, you have a slope of 0.97 and R squared of 0.99, indicating very, very good agreement between the two methods. And the same for manganese, getting a slope of 1.04 with an R squared of 1. So very, very precise relationship there. The next study that I wanted to talk about is one that was done at a national ambient air toxics trend site. This trend site was located in St. Louis, Missouri, and the study, or the samplers, were operated by the Missouri Department of Natural Resources, the state of Missouri, where St. Louis is located. This station is part of a national network that collects priority and core hazardous air pollutants, including metals like arsenic, beryllium, cadmium, chromium, lead, manganese, and nickel. The Xact operated at the site from a time period from November of 2012 through March 31st of 2014, so a period of about 16 months. So you have a very long data set, a long period of operation. And the FRM samplers were operating in a 1 in 6 day fashion, meaning that they took 1 sample every 6 days, and that 1 sample was then analyzed by the laboratory by ICP mass spec. And in this case, there were 3 different elements that were typically observed above the quantitation limits and the detection limits for the reference method. And they were selenium, manganese, and lead again as well. And for this, on the next slide, I have the results for manganese and lead. And what you can see here, again, you have a situation where the manganese filter sample from ICP mass spec is plotted on the x-axis, while the exact result is plotted on the y-axis. And you're seeing very, very good slopes here. For manganese, you're seeing a slope of 1.01, essentially nearly perfect agreement between the two methods, and R squared of 0.99. And then here you're also seeing for lead a slope of 0.93 and R squared of 0.91. And then down here at the bottom, you see a table where we have both the number of samples and the mean between this first one is the mean for the reference method, and the second one here is the mean for the exact. And statistical analysis indicates that there is no statistical difference between the mean exact concentration and the laboratory reported concentration at the 95% confidence level. So essentially, the exact and the reference method are giving we're giving the same results. Now, the results for selenium are very similar as well. So now the final study that we'll be talking about is the one that was done by King's College in London. This study involved sampling with the Xact and a reference method sampler at 3 different sampling locations. One was at a roadside site in downtown London. One was in an industrial area outside of London, and then one was at an urban background site, also in London. The Xact again was compared against ICP mass spec, and then also the researchers performed a novel comparison with the TOM, which is a form of mass measurement as well, and we'll get into that study in a few slides. The nice thing about this study is that there were quite a few elements that were present at concentrations high enough to make comparisons between the two methods. On this slide, I have 5 different elements. I have chrome, potassium, copper, iron, and manganese. All of them have slopes very, very close to 1, indicating very, very good agreement between the reference method, between the ICP mass spec, and between the Xact. And then on the next slide, I have 6 additional elements. We have nickel, barium, lead, vanadium, calcium, and zinc. And again, we're seeing very, very good agreement between the reference method and the Xact, indicating that the Xact is, in fact, comparable to standard laboratory methods, and that the data can be used much in the same way as laboratory method data can be used, at least from an accuracy perspective. And then, as I mentioned, this researchers also did a rather novel comparison between the instrument and the TOM, or the tapered element oscillating mass balance. What they did is they generated a laboratory aerosol that contained a couple different elements. They had a potassium chloride, where the Xact is able to measure both the potassium and the chloride. They had a zinc acetate, where the Xact is able to measure the zinc portion, and then an ammonium sulfate, where the Xact is able to measure the sulfur portion. And what they did is they measured the TOM mass and then calculated what the mass would be for potassium, chloride, zinc, and sulfur based on the stoichiometry of the elements that they were nebulizing, and then compared that value against the Xact. And what's interesting about this is is effectively a direct mass comparison between the Xact and a reference method, and there's no spectroscopy involved. There's no possibility of any interference. There's no digestion required for this approach either. And it also allowed us, as you'll see in the next slide, to make comparisons at much higher concentrations than you might be able to make in the ambient environment. So these are the results from the T-ohm comparison. You have the results here for chloride, for potassium, for sulfur, and for zinc. Again, in all cases, the slope is very, very close to 1, indicating good agreement between the Xact and the T-ohm measured mass. And again, the concentrations are very, very high. What you'll see here is you have concentrations going up to about 40,000 nanograms per cubic meter. For zinc, about for potassium, about the same for chloride. And then for sulfur, you're seeing concentrations up around 35,000. And for zinc, concentrations up around 20,000. So what that shows you is, one, not only that the Xact is very comparable to a gravimetric measurement, but that the Xact is making accurate measurements at very, very high concentrations. So in the study, you have a good comparison at low concentrations using ICP mass spec, and a good comparison at high concentrations using this T-ohm approach. So in summary, in terms of the comparability studies, the Xact has been compared to laboratory methods in several peer-reviewed studies, both by researchers at universities and by regulatory agencies like the US EPA, and that the Xact has shown good comparability in those studies. And what that means for you, if you're wanting to do source identification, source apportionment, is that you know that this data is comparable to data that you might get by more traditional methods, and therefore can be used very reliably. The next several slides, I want to discuss some of the quality assurance and features of the instrument, and a little bit about how the results or the concentrations that are being reported by the instrument are traceable to standards based on National Institute of Standards and Technology in the United States, or NIST. In the next several slides, I'll be talking about how the instrument is calibrated, what kind of standards are used to calibrate the XRF. I'll be talking about factory acceptance testing that we do here to make sure that each and every instrument that we send out is accurate and traceable to NIST. And then I'll be talking about, once the instrument is in the field and being used by the customer, what kind of automated daily quality assurance is available so that you as a user know that each and every data point that you are producing is accurate and can be traced back to the original calibration of the instrument. So first of all, the calibration that we have is done with standards that are traceable to NIST standards. The aerosol concentration on the Xact is determined by dividing the XRF mass divided by the total volume. So what you want is to have both the mass measurement made by the instrument, or the XRF measurement made by the instrument, traceable to NIST standards, and you want the volume measurement made by the instrument also to be traceable to NIST standards. So what we use for the XRF standards are shown in the picture here. It's a thin film disc. These standards are gravimetrically NIST traceable. They are produced by vapor deposition of a pure element, and the filter sample, or the substrate on which that is deposited, is weighed both before and after the vapor deposition, using a balance that is traceable to NIST. These standards are also recommended by the US EPA in the Inorganic Compendium of Methods as the approach to use when measuring elements in PM. And then finally, the NIST traceable flow standards are used to calibrate the flow measurement. So in that way, both the XRF measurement that we make of the metal mass and the flow measurement that we make are traceable to NIST standards. So your resulting concentration data is also traceable to those standards. Now, before we ship each instrument out, we do a very careful factory acceptance test. And in this factory acceptance test, it's somewhat unique. What we're able to do is we're able to challenge the entire instrument with a reference aerosol. And by doing that, we're able to challenge the entire system and every part of the system to make sure that it's working correctly, so that when it gets shipped off to the customer, you know that your data is valid. And that test includes testing the flow measurements in the flow system, the XRF system, any kind of leaks that are in the system, the sampling procedures that are used, the tape movement. Every portion of the instrument is tested by this approach. And the aerosol that we use is generating using our quantitative aerosol generator. And this operates by nebulizing a solution of a known concentration at a measured rate into a measured flow. And all those individual components, the solution concentration, the mass loss rate of that solution or nebulization rate of that solution, and the flow rate that that's being nebulized into, are all traceable to NIST standards. And so therefore the QUAG generated aerosol is also traceable to those National Institute of Standard and Technology standards. And then finally, this approach has been validated by the US EPA under Method 301, which is EPA's method for validating different measurement and measurement validation technologies. This slide shows some of the example results that you see with the factory acceptance test. Again, it's very similar to some of the graphs that we've seen previously. The reference aerosol concentration is on the x-axis. The exact reported concentration is on the y-axis. We do the aerosol test at 3 different concentration levels and then generate a least squares fit where we're looking for a slope very close to 1 and a high R squared, indicating high precision between the two methods. And then finally, now once the instrument is shipped out in the field, there are a number of very unique quality assurance procedures that are available on the Xact 625i. These quality assurance procedures are based on our US patents that we hold, and they include an XRF stability check that validates the XRF portion of the Xact with each and every sample, as well as an upscale test that we perform on the instrument once per day. The XRF stability check is done using a rod that is located in a fixed position underneath the filter tape in the XRF analysis area. The rod is made from niobium, and we choose that because it's a fairly rare element in the atmosphere. And then the value for that rod is determined at the time of calibration. And then with each and every sample, we monitor that for stability. And what that does is it ensures that at each data point, the concentration reported by the instrument is traceable back to the original calibration that was done on the instrument. So you know that each and every data point is valid and accurate. And then, of course, once a day, we do an upscale test as well. And in this test, we inject a rod into the analysis area, the XRF analysis area, and the rod has chromium, cadmium, and lead on it. And then this is just a further validation of the stability of the XRF system. The value for each of these elements is determined at the time of calibration, and then you're looking for a stable response each and every day thereafter. And then the advantage of this is that it tests all 3 analysis conditions that the Xact 625i uses. And now this is showing some of the results from, this shows some of the results from a field study for this kind of QA data. This is the XRF upscale check, and this happens to be data from the ETV study from the US EPA's Environmental Technology Verification Study. And then what you can see here is that the upscale never varies by more than 3%. So that indicates that the instrument is very stable. And not only that, it was very stable even after the instrument was moved. So during the course of this 145-day study, the instrument was moved from one location in East Liverpool, excuse me, to another location in Marietta, Ohio. And during that move, the instrument didn't need to be recalibrated. It was just moved from one location to another and then restarted. And then this shows the same data, but for the upscale stability check that is done with each and every sample. And what this shows is you have almost 3,500 samples, almost 3,500 samples over the course of 145 days plus a move, and there's less than 6% drift at every single data point. And this is the kind of stability that we typically see from the instrument. And that gives you as a user the assurance that the data that you're using is in your source apportionment, your source identification studies is valid. So for the next several slides, I'll be discussing in a little bit more detail source identification and source apportionment. And there are a number of different approaches to that that utilize different, number of different approaches that are utilized in terms of source identification. We use the time resolution of the instrument. You can correlate high concentrations that are being reported by the instrument with local activities. We utilize chemistry. The instrument is measuring a lot of different elements. And so you're able to compare the chemistry that is being measured by the Xact with known source chemistries. And this is particularly important in an industrial setting where maybe if you're sampling outside of a plant and you know the chemistry that's involved in the plant, you can use what's being reported by the Xact to identify what's going on and what's producing the emissions from the facility. The high time resolution of the instrument allows for correlation of elemental elements with wind direction, and we'll look into that a little bit too. And then more recently, the instrument has been used in highly time-resolved factor analysis using approaches like positive matrix factorization, or PMF. And we'll look at some of those studies as well. So for the first one, identifying emissions, looking at time resolution as an approach to that. This graph here shows a single day that was sampled on the fence line of a lead smelter in the United States. And the line down here represents the average concentration for that particular day at 4.6 micrograms per cubic meter. And what you can immediately see is that 2 1-hour time periods are responsible for the vast majority of that average concentrations. So what you're able to do is what you may be able to do is go back and identify what kinds of activities were going on during those 1-hour time periods to give you a better idea of what the sources may be. And if you were operating on a plant site, for example, you might be able to use that feedback for a process control to understand how you might be able to reduce your emissions. In other situations, you might be able to use this type of information to identify if a source is, say, maybe traffic or something that occurs at a particular time of day rather than at another time of day. It's also possible with the high time resolution to correlate wind direction with high concentration events. And if you have multiple monitors to use, you may be able to orient the sources. Well, you may be able to orient the sources so that they can be located based on wind direction. And this slide shows an example of it, of this approach as well. In this case, the Xact, again, is sampling on the fence line of a primary lead smelter, which is located here. The Xact was sampling here. And then what you see on this graph is you see the lead concentration plotted versus the wind direction here in degrees. And what you can see is that your highest concentrations are occurring at a bearing of 135 degrees, which corresponds to right here on the plant site. So in this particular study, what we were able to do is not only identify, obviously, that the plant was the source of the lead, but what particular part of the plant was the source of the lead. And that may be useful as well in the types of studies that you want to do. You may be able to identify what direction high concentrations of various metals are coming from take a look at your source inventory and identify what sources are in that direction, and then begin to use that information to identify what source in particular or sources in particular are responsible for the concentrations that you're seeing at your monitoring site. It's also possible to do source identification with wind direction with multiple instruments. There are situations where you may be able to do upwind and downwind measurements that would take advantage of both time resolution and correlation with wind direction. You can use this type of measurement to identify if a source that you're seeing for a different elemental measurement is a local source or if it's a regional source, if it's something that's being blown in from somewhere else or is originating in the city or area where you're monitoring. And if you have 3 instruments or more, you may be able to do some triangulation of the data from multiple monitoring sites to help identify the location of the source. This, I'm showing an example of one where you have an upwind and downwind location. This is done at a location where you have an industrial facility that's located in a river valley. And so essentially the wind is either blowing upriver or downriver. And you have 2 Xact monitoring sites. In this case, this is the upwind location, Xact Site 2, and this is the downwind location, Xact Site 1. And you can begin to understand the facility's contribution to the concentrations that are being measured by simply subtracting Site 1 from Site 2 and to understand what the contribution of the industrial facility is. The Xact also comes with an automated source characterization software package that we call ADAPT for Automated Data Analysis and Plotting Toolset. This software package comes with the instrument and allows for easy assessment of data collected on the system. The Xact also comes with a MET sensor, a wind speed and wind direction sensor. And that data from that sensor is automatically incorporated into the data from the instrument. So there's no need to try to make sure that your MET sensor that you have independently is timed perfectly with your instrument measurements and things like that. It has a very user-friendly interface. And what it does is it creates some graphical displays that will help you as a user to identify sources based on their time resolution and their chemistry and the meteorology of the area. And we'll show some of the slides from that software in the next couple slides, some portions of that software in the next couple slides. This one is from the time of day trends feature on ADAPT. There are a number of other features as well, but we're going to look about 4 of them. And in this time of day feature, what you're trying to do is identify time periods where you have high concentrations. And here what we have is if you select nickel, which is what's selected here, and you have each individual hour of the day from midnight to 11 o'clock over the time period, which can be user selected here. This would be a drop-down menu in the software where you'd be able to identify the date or the time period in which you want to take a look at. And what you have, this is a bar and whisker plot. So it's showing here, this is the highest concentration for that particular hour period. The box represents the concentrations that fall between the 25th and 75th percentile. And then you also have the average and mean values reported in here as well. The primary information that you can get from this, though, is you begin to understand what kind of diurnal patterns you have for particular elements. In this case, for nickel, you're seeing the highest concentrations occurring during the middle of the day, probably looking at a source that is like a manufacturing source or something that is operating the most during the middle of the day. You also may have other types of patterns that you might see for if you have elements that are associated with traffic, like barium might be associated with brake wear. You might see a more diurnal pattern in that kind of case where you have a high concentration associated with morning rush hour and another peak concentration associated with evening rush hour. But what this plot will allow you to do is immediately see what that pattern is. And I think the key point here with the ADAPT software is that those plots are created essentially automatically. You don't have to import the data into Excel or some other MATLAB or some other kind of data analysis package. It's done right on the instrument, and it can be done in a matter of minutes rather than taking hours or days of someone's time to generate the data and to generate the plots of the data. This is another similar kind of plot. This is a day of the week trend. And what you have here is each day of the week. On the left-hand side, you have Monday through Sunday. The highest concentrations are indicated by the darker red values. Lower concentrations are represented by the deep blue values. And what you can begin to identify is for each individual element, in this case, this is zinc being plotted over here, over your selected time period, you can identify what days of the week and what hours of the day have the highest concentrations, and that can give you information about the sources that are involved. Again, the highest concentrations are typically, in this example, during the day and during the work week, so you probably have a source that is, something like an industrial source operating during normal business hours. This particular slide shows the correlation matrix feature of ADAPT. And what you can do with this is automatically, for each element that you select, in this case, vanadium is selected, you can plot it against the concentration of every other element that's being measured by the Xact. And in this case, if you have a high R squared, that indicates that those elements are highly correlated and maybe from the same source. In this case, you have vanadium. It's highly correlated here with cobalt. This is cobalt here, CO. And then this 0.76 is the correlation coefficient. So it's indicating a high degree of correlation between vanadium and cobalt. It's also indicating a high degree of correlation between vanadium and nickel. So the vanadium, nickel, and cobalt may all be from the same source because they are so highly correlated at the monitoring site. And then finally, this slide here shows essentially the wind directionality information from the instrument. So this is a way of plotting the high concentrations versus the wind direction that you're seeing. So in this particular case, what you're seeing is you're seeing high concentrations of cobalt coming from two different wind directions. What's interesting about this particular feature is that you're actually able, via some feature like Google Maps, be able to put down the actual map of where you're located and then be able to see the wind, what's around you from that particular wind direction where the monitoring site is. So in this case for cobalt, what we're graphing is the highest concentrations here. They're coming from two primarily different wind directions like this. Obviously with this building in the way, that's probably a contributing factor for that. In the next several slides, I'm going to be talking about how the Xact has been used much more lately in the past couple of years in source apportionment studies. It's been involved in a lot of source apportionment studies over the last few years, primarily source apportionment of either total PM 2.5 or PM 10. In those kind of cases, the Xact data is being used in conjunction with other measurements, obviously a measurement of total PM mass or total PM 2.5 or total PM 10 mass, but also other instrument data, maybe data from an OCEC monitor, organic and elemental carbon, maybe data from an ion instrument measurement, that's something that's measuring secondary aerosols like sulfates and nitrates, may also be used in conjunction with something that measures organics and things like that, so that you can get some source apportionment based on that. And although metals typically constitute a very small percentage of the total PM, they are very often the key tracers that are used in identifying where that PM is coming from. So again, this is the metals part of it, part of the measurements that you're making when doing a source apportionment study have a very outsized role in terms of their apportionment, in terms of apportioning the total mass, because these elements are such key tracers for different sources. In addition, we've also seen some source apportionment being done, excuse me, just on the total metals themselves. Since metals are often highly reactive, they can have a pretty big influence on the health effects of air pollution. So there is some interest in doing source apportionment on just the metals themselves as opposed to PM10 or PM2.5. One key factor, though, that people are finding with this high time resolution measurements being made by the Xact and other field instruments is that you can begin to get a statistically robust data set in a much, much shorter period of time. If you're going to do a factor analysis approach like PMF, you need a large data set to get good, reliable results. And you can get that much more quickly with high time resolution measurements, with hourly measurements that are made, for instance, with the Xact or with other high time resolution instruments like OCEC instruments or mass spectroscopy instruments. More data can allow for segmentation of the receptor of your receptor data prior to factorization. We've had studies where data was, because there's so much data available, they can segment their study based on the seasons or wind direction or precipitation even prior to the factorization process, even prior to performing PMF. And what they found is that different seasons can have different factors or different sources that are associated with that season. This particular example, there was a study that was done in Korea that demonstrated this. It was done by the National Institute of Environmental Research in Korea. We've also had some studies that show how you can get some confirmation of your factors of a source based on their diurnal variability. Now, if you had a filter sample where you're just getting one sample per day, you wouldn't be able to see that diurnal variability. But with the Xact, when you're getting hourly samples or even higher time resolution samples, you can see that kind of diurnal variability and begin to identify sources or be able to factor your PM measurement much more because you have more hourly information. So we have a sample here from Toronto, a Canadian roadside study. And what they were able to do, the University of Toronto was able to do, is they were able to identify traffic sources based on the diurnal variability of their sources and the effect of humidity on road dust. So they were able to resolve things like braking factors from tailpipe emissions based on the time resolution. So for example, we're seeing much more a braking factor much more present at time periods during rush hour versus free traffic when the tailpipe emissions were a much larger part of PM. You're also able to use highly time-resolved metals data for better resolution of factors than could be identified based on longer time data. There was a study done by a university in Hong Kong that showed this. They were able to identify 8 factors rather than 4 or 5 factors based on the Xact data and based on the high time resolution data. So what that means practically is that you can have a much better understanding of the airshed that you're studying and be able to identify more specific factors that contribute to the PM10 and PM2.5 concentrations that you're seeing in that airshed, and then be able to use that information, hopefully, to control those sources. Also, you're able to, because you have high time resolution, we've talked about correlation of a particular element with the wind direction. After you perform the source apportionment or the PMF analysis, you may also be able to do correlation of a specific factor with that wind direction. And there's been some studies out of China published in the Atmospheric Chemistry and Physics that have shown this to be the case as well. We've also had some researchers take some additional steps in their source apportionment. In particular, we've had a group out of the Paul Scherrer Institute in Switzerland who uses the Xact 625. They do some size partitioning with the instrument. They're able to take samples of both PM10 and PM2.5 sequentially. So they'll take a, say, PM10 sample 1/2 hour, and then the next half hour take a PM2.5 sample. And that size fractionation can help with the identification of the source. So for instance, if you have a much smaller size, if an element is present much more in the PM2.5 phase, that indicates maybe its source is more associated with combustion. In PM10 phase, it's associated more with the mechanical. And the instrument, what we're able to provide with the Xact is we're able to provide a signal that can be used to toggle the valves that you see here. These two red things are valves. The instrument can automatically send out a signal that will allow the user to toggle back and forth between these two different sampling pathways. And then the researcher, of course, can use that information to help identify the source based on what size fraction is in predominantly. And then, as I mentioned earlier, we also have a fairly new feature on the instrument. We are now able to do time resolution as low as 5 minutes. And what this does is it allows the instrument to be placed in a moving vehicle, and you can identify and correlate high concentrations of metals with specific geographic locations. And we've actually had an agency, the South Coast Air Quality Management District, which is the agency responsible for air pollution regulation in the greater Los Angeles area. They used the instrument very briefly for a study where they were able to find numerous metals sources that hadn't been located before simply by placing the instrument inside of a moving vehicle and observing the geographic locations where they had high concentrations. And then presumably what you're able to do then afterwards is go back to those locations and do more extensive monitoring and really begin to identify and nail down what specific sources or what specific sources are responsible for the concentrations that we're seeing. So in this way, the instrument can be used very quickly as a screening tool to identify what areas of your airshed you might have more interest in monitoring. And then, as Anna had mentioned at the beginning of this presentation, there are several source apportionment studies involving the Xact already going on in India. So the instrument is being used to understand air pollution in India currently. There have been 4 groups so far that have used the instrument in India. IIT Delhi is using one that's for a study that's going on in the Delhi metropolitan area. The study is currently ongoing. They're still gathering data. IIT Kanpur is also participating in the study. They're also monitoring in the Delhi metropolitan area. Washington University, which is a university based in St. Louis, Missouri, cooperated with the Delhi Pollution Control Board on a study that did some monitoring outside of National Stadium in Delhi. And their data collection was completed in early 2020, and they're, I'm assuming, currently working on some of the results of that. And then finally, the Paul Scherrer Institute in Switzerland also did very briefly some data collection in January of 2019. So the instrument has had some experience now operating in India. It operates very well, and the users are being able to begin to identify some of the sources that are responsible for air pollution in India. Now, if on the last couple slides, just to kind of give you a sense for how the Xact is being used. It's been used pretty widely. We have just about 200 installations globally. It's used by a wide range of government agencies like the US EPA, Environment Canada, the Ministry of Environment in Ontario, California Air Resources Board, South Coast Air Quality Management District, National Institute of Environmental Research, Queensland EPA in Australia. So it's got quite a list of government users. It also has quite a list of university users as well. As I mentioned, both the Indian Institute of Technology in Delhi and in Kanpur are using the instrument. The University of Toronto has one, or several, King's College in London, University of Birmingham, University of Manchester, University of Massachusetts, Peking University in China. So the instrument is being used very, very widely by lots of different researchers, by lots of different government organizations. And this kind of, this indicates that the instrument is beginning to be fairly widely used and accepted by the broader environmental monitoring community. And then this is some of the journals where data from the Xact has been published. It's been published in the Journal of Air and Waste Management, Atmospheric Chemistry and Physics, Atmospheric Measurement Technologies, Atmospheric Pollution Research, Journal of Geophysical Research, Science of the Total Environment and Atmospheric Environment, as well as other journals. Again, this indicates that it's beginning to, the instrument and the data produced by the instrument has been pretty well accepted now at this point by the broader scientific and monitoring community. So finally, in summary, the Xact provides highly accurate, highly time-resolved metals concentration data. The Xact is comparable to reference methods for measuring metals. One key point is that the automated quality assurance procedures help assure that the data that's being used by the user is accurate, reliable, and traceable to the original calibration. And that means that you can then trust that data to be useful in your source apportionment and source identification studies. And then finally, the Xact also comes with this ADAPT software package that will help very quickly identify sources without a lot of the work that's required in terms of data visualization. And so with that, we can look at some of the questions that have been put in and hopefully begin to answer some of them.
Thank you, Greg. Thank you for a very good presentation. So there are a lot of questions. I will read through certain questions. We will answer a few. So one is about interferences. So basically, is there any matrix interference while sampling in polluted environments? And what are the general issues observed while sampling in polluted locations?
So in very highly polluted locations, like you might see in various cities in India, the principal thing may be that you may not be able to sample at every time interval. You want to maintain 16.7 liters a minute while you're sampling so that you have the appropriate size cut. And if the PM loading gets too high on the filter tape, then you may not be able to maintain that. Now, we have a fair amount of experience in India at this point, and for the higher pollution events, we're seeing that you can still sample most of the time for 1 hour. Maybe at the various very, very high pollution events, you may want to look at sampling for half-hour time intervals. So that's the principal issue that gets associated with sampling in a very polluted environment.
Yeah, thank you. So one more question is, like there are many elements that are used in QA and QC checks. Like how confidently we can use it in PMF analysis? Like for example, like NB, niobium.
So we typically use niobium as a QA element, which means that you can't really use that in your source apportionment data. But we're not necessarily, you may be able to choose, and in fact, we used to use other elements as well. So you may be able to choose a different element that you don't suspect is present in your airshed and use that as a QA element instead of niobium. The key point is, though, that by having an XRF stability check, you're able to know that with each and every sample that your XRF portion of your instrument is performing correctly, and so that you can have confidence in using the data from each and every hour in your source apportionment study. And that, I think, is the most important feature that you have. You know when your instrument is operating correctly because you have data being produced by the instrument to show that.
Yeah. So one more question is about like whether the instrument is tested at varying temperature and RH conditions. Like what is the effect of RH on the performance of the instrument?
I'm sorry, can you repeat that? I couldn't quite hear you.
Is the instrument tested at varying temperature and relative humidity? So like what is the effect of relative humidity on the performance of the instrument?
So in terms of the relative humidity, the instrument comes, first of all, should be housed in a temperature controlled environment. So it's typically housed in either a shelter or something else like you would typically see for most other types of ambient monitoring equipment. And the temperature in that shelter should be maintained fairly reasonably around room temperature. And then when you're sampling in a very hot and potentially very humid environment, like you might see at various locations in India, it's important to maintain a temperature that will keep water from condensing on the filter tape. And that's the primary concern when making metals measurements, is that you just want to make sure that you don't have any liquid water falling out in your tape. And we have a number of heaters that prevent that from occurring. In terms of, we don't at this point make a PM mass measurement. And in a PM mass measurement, it's much more important to maintain a specific relative humidity, usually around 35% relative humidity. With metals measurement, though, that's not of particular importance. The only thing that's really of importance is to prevent liquid water from getting onto the tape. And the heaters are able to prevent that.
So one more is about offline sampling. So is there any module in addition to Xact that can do offline sampling, like, or for the rainwater analysis as well? So like, is it the only way through nebulizing it and depositing it onto a filter tape?
In terms of rainwater analysis, I probably would recommend that you do, we have a version of the Xact called the 920 that's intended for water analysis. And in that case, what we do is we take a sample, like if you had a sample of rainwater, and we would nebulize that and dry it and then sample that onto the filter tape. And that would be an approach that would work very well for taking rainwater samples. And you may even be able to devise a system where you might be able to even take rainwater samples on a fairly continuous basis from, from a trough or a gutter or something like that. In terms of samples, individual samples, you can measure individual air samples if they are sampled onto like a PM2, if they're sampled on a Teflon filter of 25 millimeters in diameter. You can make individual filter measurements on the instrument using an approach like that as well. So you can use rainwater if you use the Xact 920, which is designed to measure water, or if you want to do some individual samples and make measurements with XRF, you can use a 25 millimeter filter and measure ambient particulate that way as well.
About this like Xact version that can measure water, we will be coming up with one more talk, probably within a week, or we will let you know about the schedule. So probably that time we will be discussing in detail about the version of the Xact that can measure water as well.
Yeah, so, definitely.
Yeah, and actually there are a lot of questions, so we have already passed the time. So what we will do is probably we'll personally contact each and everyone with the questions, and we'll be able to answer them after the session. Thank you, Craig. Thank you for the session. Yeah.
Yes, thank you, and I appreciate everyone's time. Thank you for coming out, and hopefully, if you have questions, please feel free to contact me or free to contact Anna at Tescorn, and we'd be happy to get back with you.
Yeah. Thank you, Craig. Thank you, everyone.